In the early 19th century, the prevailing consensus in chemistry was that the carbon skeleton of a molecule remained completely static during a reaction. Subsequent discoveries dismantled that theory. Chemical species are highly dynamic, and they frequently undergo deep-seated structural reorganization during transformations. Understanding this self-reorganization, specifically the 1-2 shift, reveals exactly how molecular frameworks naturally tear themselves apart and reconstruct to find their absolute lowest thermodynamic energy state. This 3D animated diagram illustrates neopentyl bromide undergoing solvolysis. Notice the massive tert-butyl group next to the primary carbon. That immense steric bulk acts as a physical wall, actively repelling any approaching nucleophile and blocking standard SN2 substitution. Cut off from a concerted backside attack, the molecule is forced into an SN1 pathway. The bromide leaving group departs on its own, leaving behind a highly unstable primary carbocation, highlighted here by the intense, localized positive charge. High-energy intermediates, like a primary carbocation, are extremely unfavorable. To survive the reaction and stabilize that positive charge, the molecule guarantees that an immediate and drastic skeletal shift must occur. This 2D structural diagram maps the exact mechanics of a Wagner-Meerwein shift. To resolve the instability, an adjacent methyl group detaches from its original position and slides over to the adjacent empty p orbital, taking its entire bonding electron pair with it. Pausing halfway through this migration reveals a 3-membered cyclic transition state. Because the migrating methyl group brings its bonding pair along, this tight cyclic array contains exactly 2 interacting electrons. A 2-electron system satisfies Hugel's 4n plus 2 rule for continuous pi systems, where n equals 0. This configuration gives the transition state formal aromatic stabilization, which lowers the activation energy needed to execute the shift. The immediate outcome is a tertiary carbocation framework, which is vastly more stable than the primary starting point. From this state, the molecule can safely capture a solvent nucleophile or lose a proton to complete the reaction. Isotopic labeling studies confirm that under mildly basic conditions, this reaction yields a 36% proportion of rearranged alkene. The intramolecular shift is so energetically favorable that it physically outpaces the speed of external solvent attack. This hierarchical flowchart introduces the concept of migratory aptitude. When multiple different groups surround a reactive center, the group best able to bear and stabilize a positive charge will shift first. Hydrogen possesses the highest aptitude, followed by phenyl, then tertiary, secondary, primary, and finally methyl groups. We can apply this rule using this 2D structure of an unsymmetrical 1,2 diol from the pinocol rearrangement. The water molecule is preparing to leave, which will generate an electron-deficient carbocation. The adjacent carbon holds both a phenyl group and a methyl group. You must deduce which will migrate. The phenyl group migrates. As it shifts toward the positive charge, its aromatic pi electron system provides resonance stabilization to the transition state, outcompeting the methyl group. However, molecular geometry and spatial crowding can override charge stabilization, especially in conformationally rigid or cyclic systems. This 3D Newman projection of a locked cyclic system demonstrates the geometric law of migration. To achieve the necessary orbital overlap, the migrating group must adopt a precisely antiperiplanar 180-degree transdioxial alignment relative to the departing leaving group. When evaluating a rigidly locked molecular framework, the antiperiplanar requirement dictates the reaction. A stereoelectronic mismatch will prevent migration entirely, regardless of a group's inherent electronic migratory aptitude. These migrations are not restricted to carbon skeletons. 1,2 shifts can occur toward other electron-deficient centers, as seen when carbon migrates to oxygen in the Baeyer-Villiger oxidation, or when it migrates to nitrogen in the Beckmann rearrangement. The Beckmann rearrangement operates on a massive industrial scale. It is the exact chemical pathway used to convert oximes into the specific amides and lactams necessary to manufacture nylon polymers. Molecular rearrangements are highly reliable, programmable chemical tools. By controlling the conditions of the 1,2 shift, researchers synthesize complex pharmaceutical compounds and drive global material science. This dynamic checklist summarizes the 3 master rules for predicting structural shifts. First is thermodynamic pull. Structural migrations are driven by the molecule's need to stabilize a positive charge, relieve steric strain, or achieve rearomatization. Second is migratory aptitude. When multiple groups can move, they follow a hierarchy of charge stabilization, moving from hydrogen down through phenyl, tertiary, secondary, and primary groups. Third is the anti-periplanar law. In rigid frameworks, proper 180-degree orbital alignment is the mandatory physical requirement for a migration to occur. By strictly applying these three mechanical laws, you can accurately track the movement of electrons and determine the specific connectivity of the final rearranged product.